Exercise 1202 is on discrete probability distribution. So we're going to learn here exactly what these things are. So first of all, they list the probabilities for each value of a discrete random variable. All possible values of x must be mutually exclusive. All probabilities add to 1, and each probability is between 0 and 1. So here are some examples. We're asked to draw a histogram for each of the distributions below. So here's a probability distribution. It lists the probabilities for each of the values there. So the probability of getting 1 is 0.3, the probability of getting 2 is 0.1, the probability of getting 3 is 0.2, and the probability of getting 4 is 0.4. And you'll notice if you add all of those up, they equal 1. Okay, so 0.3 plus 0.1 plus 0.2 plus 0.4, that equals 1. Okay, so let's have a go at drawing this histogram. So a histogram, we have, what you might notice is that on my y-axis, I've got the values up to 0.4 because that was our highest value. On my x-axis, I've drawn my first little mark, 1 unit in, and then I've left gaps of 2 units each. So each column is going to be twice the size of that gap. So let's have a go at drawing it. So for 1, we have 0.3. So this is 1, 2, 3, 4. And I go up to 0.3, across 2 squares, and down. For 2, I need to just go up to 0.1, so I'm going to go across here and down there. I need to go up to 0.2 for 3, so up there, across, and down. And then for 4, I need to go up to 0.4, so up there, across there, and down there. And there's my histogram. For this second one, now this one, it should be noticed firstly that each probability is the same. So this is what we call a uniform distribution. If each probability is the same, it's uniform. And when I draw my histogram for this one, they're all going to be the same height. So we know it's uniform. So we go up to 0.25 and across for all of them, and down, and join each of those up. So when you have a uniform distribution, you get a rectangle, which is quite nice. Okay, question 2, draw up a probability distribution for each of the following and show that they are probability distributions. So what we see here is we've got some values for x and some frequencies. So we've got our x, we've got the probability that we're equal to that value of x. We've got 1, 2, 3, 4 across here. And then we've got the probability of each one. So to do that, we do need to know what the total is. So we need to add those up. So 10, 20, 30, 40, 50, 60 is the total. So this first one is 15 out of 60. I've just left space there to simplify. So dividing by 5, that's 3/12. For the second one, it is 12 out of 60. I'm going to divide by 6, 2/10, so 1/5. For 3, it's 23 out of 60. 23 is prime, so that's not going to simplify. And for the fourth one, it is 10 out of 60, so 1/6. Now you can do that as a decimal or a fraction. Now we do have to verify that it is a probability distribution, and the way to do that is to add them up. Now the easiest way to add these up is to leave them out of 60. And of course that is going to work because the way we got the 60 was to add up those numerators. So we can see here easily that's 60 out of 60, which is equal to 1. So it is a probability distribution. Each probability is between 0 and 1, and they all add to 1. Okay, in this example, we're given it in our function notation. So we can see the possibilities here for x, 0, 1, 2, 3, and 4. It's going to be 0 for any other value. We don't need to include that. And the probability there. So when x equals 0, we're looking here on the first line, okay? And we plug the number into our function. So we plug it into this. So if I put 0 in there, this is 3 minus 0. I've got 3 on 10. For 1, I'm using the same one, so plug 1 into the bracket, so I get 3 minus 1 is 2, so 2 tenths, or 1/5. When I do 2, I'm now on the second line, so I'm plugging 2 into this. So 6 minus 2 is 4, so it's 4 on 20, which does simplify down if I divide by 4 to 1/5. When I'm 3, I'm on the third line, so in the brackets, the 4 minus 3 is 1, so 1/5 times 1. So you can see those three are equal. For 4, I'm back on the second line again. So 6 minus 4 is 2, so 2 on 20 or 1 on 10. I have to verify that it is a probability distribution. So 3 on 10 plus 1/5 plus 1/5 plus 1/5 plus 1/10. If I add those up, I've got 3/5 in the middle there, which is 6/10, plus 7/10, 10/10. So yes, it is. Each one is between 0 and 1, each individual one between 0 and 1, and the total equals 1. Okay, consider this probability distribution. Find the value of p. So we've got 3p plus 2p plus 5p plus p plus p equals 1. So that's 12 p's on the left. So 12p equals 1, and p equals 1 on 12. So we've got 3 twelfths here, 2 twelfths there, 5 twelfths, 1 twelfth, and 1 twelfth. And each of those is between 0 and 1. So yes, it is a probability distribution, and p is equal to 1 on 12. Now for that same one, we need to find the probability that x is less than 3. So what we're doing is we're adding these two together. So we've got 3p plus 2p equals 5p. So that's going to be equal to 5 times the 12th, so 5 twelfths. For the second one, the probability that it's between 2 and 4. Now you'll notice here it does include 4, but it doesn't include 2. So what we're looking at there, I'll just write some more working out here, is the probability that it equals 3 plus the probability that it equals 4. Whereas this first one was the probability that it equals 1 plus the probability that it equals 2. Okay, so in this one, the probability of 3 is 5p, the probability of 4 is just p, so that's 6p, or 6 on 12, which equals half. The probability is less than or equal to 4. Okay, there's a little trick to this one. The probability that x is less than or equal to 4 is actually equal to the probability of 1 minus the probability that x equals 5. It's everything except for that 5. So it's 1 minus a 12th. Okay, so 1 minus 1/12. So that's equal to 11 on 12. The probability that x is greater than or equal to 3, so that's just 4 and 5. So that one is just the probability that x equals 4 plus the probability that x equals 5, which equals 2p, or 2 on 12. And we should always simplify it, so 1 on 6 is the answer there. Okay, we have to draw up a probability distribution for the number of red balls drawn from a bag containing 5 red and 2 green balls if 2 balls are drawn without replacement. So to do this, I'm actually going to start with a tree diagram to work out the probabilities. So we do have red balls and green balls. On the first draw, the probability of red is 5/7. There are 7 balls total. So green is 2/7. Remember, they have to add to 1. 5 on 7 plus 2 on 7 is 1. On my second draw, now on my first branch here, the chance of red has decreased because there are only 4 reds left in the bag, and there are 6 balls now left in the bag. Now, I could simplify that. I'm not going to, because it's easier to add things up and multiply things when our denominators are the same. This is 2 6, because 2 6 and 4 6 add to 1. And also 2 green still in the bag out of 6 still in the bag. Down here where green came first, I still have 5 reds in the bag, but I now have 6 in the bag, and I still have 1 green out of 6 in the bag.
So I just need to work out these probabilities now. So the chances of 0 reds, well, that's got 2 reds, this has a red, this has a red. This is the only line here with 0 reds. So I just need to multiply these.
That's 2 times 1 over 6 times 7. So 2 on 42. I could also simplify that to 1 on 21. The probability of 1 red, so that could be red, green, or green, red. So I've got 5 times 2 over 6 times 7, and 5 times 2 over 6 times 7 again. So that is 2 times 10 on 42. The 2 on the 42 can change to 1 on 21, so 10 on 21. And finally, for 2 reds, that's the top ones. So that is the 5 times 4 over the 6 times 7, so 20 on 42. I can also simplify that down to 10 on 21. So those are my probabilities for each of those. We need to put those into a table. So the chance of 0 reds was 1 on 21. The chance of 1 red was 10 on 21 and 10 on 21.